Today we're going to talk about factoring, and specifically because we're going to be working on factoring for a while because there's lots of different types and we want to move through and give you plenty of practice on each. So today we're just going to talk about factoring with what's called GCF for greatest common factor and special products. So we've got three goals. We want to be able to identify and factor the GCF of the terms in a polynomial. We want to be able to factor a difference of two squares and factor a perfect square trinomial. Now, before we get into the factoring, in example 1, we have a review of simplifying radicals because some of you struggled with this when it was on your last review worksheet and you did not remember how to do these. So we're putting these back in here again because after factoring, this is going to be vital. Because being able to simplify a square root answer is going to be one of the things we have to be able to do. So just to review this really quick, remember that you have two options. You can either choose the biggest perfect square method, or you can choose the factor tree method. So I will show you one of each with A and B, and I never care which way you choose as long as you show all your work. So biggest perfect square method, we use and look and we decide what is the biggest perfect square that our number is divisible by. So 27, the 16 is the closest perfect square, but it's not divisible by 16. Actually 25 would be, but it's not divisible by that either. And so the biggest perfect square that we do find that 27 is divisible by is 9. So what we do once we've decided which perfect square is our winner is we rewrite our radical 27 as 9 times, and then whatever it is that we would multiply 9 times to get 27, which in this case is 3. The reason why we do that is because once we've separated it into factors, so that's why this ties into factoring, 9 and 3 are a set of factors for 27, we can give each factor their own radical. And the purpose of that is because the one that's a perfect square is then going to simplify. So the square root of 9, we all know is 3. Square root of 3 does not simplify, and so it stays inside the radical. So 3 radical 3 would be our answer there. So that's the biggest perfect square method. The other method is the factor tree method. So you take your number, in this case 24, and you write it broken down into any set of factors. So the one that popped into my head first was 6 and 4. But certainly if you thought of 2 times 12, you can write the 2 here and the 12 here. You'll get the same final answer as long as you do all your steps correctly. Remember that you have to keep making branches on your tree until the number at the end of the branch is prime. So 6 is not prime. It breaks down into the factors 3 and 2. 3 is prime, so is 2. Their only factors are 1 in themselves. So these branches are done. So now I look at 4. 4 is not prime. And so it breaks down into 2 times 2, which is also prime. And so these 4 numbers are at the ends of my branches. Once you've done the tree, then what you're looking for are matching outfits. So I've got 3 2s here, but you can only have pairs. So pick any 2 of those to match up as a pair. And when they have this matching outfit, remember that that means that they get to go outside the house, that is the radical. They get to go to the matching outfit party. But when they go to the matching outfit party, they're no longer 2 individuals, they are 1 couple. So 1 2 only gets to go to the outside. So that takes care of the matching outfits. They get to go outside the house. This 3 and this 2 do not have anyone to match outfits with because their outfits don't match. They're not the same. So that means they both have to stay inside. And whenever you have multiple things, either on the outside or the inside, we multiply them together. So we do the 2 that's left times the 3 that's left to give us 6. So 2 Radical 6 would be our answer there. Then for C, we have a fraction under our radical. So when that happens, our first step is generally to see if we can reduce the fraction at all. So in this case, 50 isn't evenly divisible by 4, but they are both divisible by 2, which could help us. So one option is to just write them like this and simplify individually. The other option, that's why I'm going to write an or here, is to simplify first. So when I do that, they're both divisible by 2. That gives me radical 25 over 2. And then I would give them each their own symbol. So radical 25, radical 2. Now, when I do that, in the top version, the square root of 4 is 2. And then the square root of 50, I can simplify, again, either using my factor tree method or my biggest perfect square method. Let's say that I use my biggest perfect square method, so that's radical 25 times radical 2, because 25 times 2 gives me 50. And then square root of 25 is 5, so I get 5 radical 2 over regular 2. Do not try to reduce a radical with a plain number. You can't. Plain numbers with other plain numbers, radicals with other radicals, but 5 and 2 don't have any common factors, so this would be our answer. So that's one way to do it. If I do it this way, then I get to simplify the square root of 25 to a 5 right away, but I'm stuck with this radical down in the bottom. And that lends us to one of the rules of radicals, which is that you are not allowed to leave the radical in the denominator of a fraction. And the way that we undo that is by simply multiplying both the numerator and denominator by whatever the radical is that's stuck there. Because, as we discussed when we first learned radicals, the rule is that any radical multiplied times itself gives you that same number but without the radical symbol. So if you look, if I multiply now straight across, 5 times radical 2 is 5 radical 2. Radical 2 times radical 2 is plain 2. So we end up with the same answer that we got from the top. So just showing you two different ways that you could arrive at the same answer there. Okay, so now that we've reviewed that, let's look at our factoring GCF. Up here, we have a reminder that to factor a number or expression means to write it as a product, that's multiplication, of its factors. So again, when we wrote 27 as 9 times 3, that is factoring. But here we're factoring polynomials. So the steps to factoring GCF, which GCF factoring is like reversing a distribution. So we're undoing a distributive property, essentially. So the first step is to find the biggest number that divides evenly into each coefficient and constant. So that's going to be our first step. So I'm going to look here at A and look at just the coefficient and the constant. So I'm looking at 36 and 24 and trying to decide the biggest number that divides all of them. So I look at 36 and I know for sure that it's divisible by 6, but is there something bigger? So factors of 36, I have 1 and 36, 2 and 18. So is 24 divisible by 18? No. So then 3 and 12, 24 is divisible by 12. So our step 1, the biggest number that evenly divides both of these, is a 12. So I'm going to put that 12 out in front. Then step 2, find the smallest degree of variables that are in each term. And here's a hint. if there's a constant, meaning a term that doesn't have a variable, then there's not going to be a variable part to the GCF. So I look here, this guy has a y, but this guy doesn't. So I can't have a variable GCF, which means it's just the 12. So now I've written that GCF. Then what I do is undo the distribution. So I write a parenthesis, and then I kind of work backward. I say, okay, what would I multiply 12 by to give me back 36y? Well, 12 times 3 would give me 36, and then I would need the y, so 3y. Then what do I multiply 12 by to get negative 24, which would be negative 2? And then you always mentally check your answer. When you factor to GCF, if you distribute, you should get back your original. If you don't, then you've done something wrong. So I check it. 12 times 3y is 36y. 12 times negative 2 is negative 24. And so I know that this answer is correct. All right, I am going to illustrate one more for you, and then you guys are going to try C yourself. So first thing I do is look at the coefficients and or constants, so meaning just the numbers. So 4, 6, 10. So they're definitely all even numbers. 10 and 4 are not divisible by 6. 10 not divisible by 4, neither is 6. So that means that 2 is the biggest number that evenly divides all of them. So that's going to be my number part of the GCF. So step 1, 2. That's the biggest number that divides them all. Then I'm going to look at the variables, and I'm going to find the smallest degree that are in each. So 5 is my biggest degree, 3, then 2. 2 is the smallest degree. Since both of these are bigger than 2, then that means that they have at least that many x's in them. So the smallest degree is what I take out. So I take out an x squared. So then I have to undo the distribution. So I write my parenthesis, and then I ask myself, what do I multiply 2 by to get 4? So that'd be 2. And what do I multiply x squared by to get x to the 5th? Remember that when we multiply, we add exponents. So this would be an x cubed, because 2 plus 3 is 5. So now I move on to my next term. What do I multiply 2 by to get negative 6? That would be negative 3. And then what do I multiply x squared by to get x cubed? That'd be just a plain x. Final term, what do I multiply 2 by to get 10? That'd be a plus 5. And x squared, this already has an x squared, so I don't need any more x's. Always check by redistributing. 2x squared times 2x cubed is 4x to the 5th. 2x squared times negative 3x is negative 6x cubed. And 2x squared times 5 is 10x squared. So I know that I've done it correctly because I mentally redistributed and I got back my original. All right, so this one has parentheses around it. That doesn't change anything. We don't need the parentheses there, so you can really ignore them. So you're going to do the same thing that I just did in both A and B. You're going to look first to see the biggest number that evenly divides them all. Then look to see if there's a variable that can go into all of the terms, and you're going to factor out your GCF. Check it by redistributing. So go ahead, factor this with your GCF factoring. All right, so let's check your work. So when you look at 15, 10, and 5, the biggest number that evenly divides all of those is 5. Then when you look for the variables, I have a constant. And just like it says in step 2, if there's a constant, there is not a variable part to the GCF. So 5 is my GCF. So now I work backward. What do I multiply 5 by to get 15w squared? So that would be 3w squared. Then what do I multiply 5 by to get 10w, which is 2w? And then what do I multiply 5 by to get -5, which is -1? Always double check. So take this 5, mentally redistribute it to make sure you get back the original, which we do, because that helps you to check your work. All right, so now we are going to look at the factoring special polynomials. So this ties right into what we did in activity 25 when we multiplied, and we learned the two special patterns, difference of squares and square of a binomial. These are those same exact patterns, except now we're working in the opposite direction. So the difference of two squares in activity 25, we started with this pattern. Two parentheses that were identical except one a plus and one a minus, and we learned that the shortcut was to write that as square the first one, minus sign, square the second one. Notice that perfect square trinomial is created by the square of a binomial. So same exact pattern. We will typically call a perfect square trinomial a PST for short, just like we say GCF for greatest common factor. But this is the same pattern that we used when we have perfect squares on both ends, and the middle is double the product of the square roots of those perfect squares. So here's the thing. When you are looking for special polynomials, a difference of squares always starts as a binomial. So don't try to factor something with this pattern if it's not a binomial. A PST trinomial is part of the name. So that can help us to narrow these down. So I'm going to look at some of these with you. The pattern for difference of squares. We have two perfect squares on the ends separated by a minus sign. So that's what I'm looking for, and it has to be a binomial. So binomial, binomial, binomial. These are the ones we should be checking. So is x squared a perfect square? Yes. And what I usually do is I write the square roots when I'm checking right above. So the square root of x squared is x. Then I look at this guy, 25. Is that a perfect square? Sure is. So I write that underneath. Then I check, is this a minus in between? Because that's part of the pattern. Yes, that is a minus. So that means that this is a difference of two squares. So I'm going to factor it with this pattern. I take square root of the first term and I put those in the fronts, both of my parentheses. Then I take the square root of the second term, which in this case is 5. I put it in the back of the parentheses. Then I give one of my parentheses a plus and the other a minus. Does it matter which one? No. If you put the minus first and the plus second, that's still 100% correct, and that works. Here's the other thing about factoring. You can always know if it's right, because if I FOIL this back out, I should get back my original. So there's always a way to check. So if you're saying, I don't know if it's right, you should know if it's right, because if you FOIL it back and you don't get the original, then it's not correct and you need to look at it again. All right, so now we're going to look at B. And so what I want you to do is to look and say, okay, does this fit my pattern? So do both of my terms have a perfect square root? So square root of 4, yep, that's 2. Square root of x squared, that's x. Square root of 9, yep, all perfect squares. So is it a minus in between? Yes, it's a minus in between. So what I need you to do now, I've already written out what the square roots are for you. I need you to write this pattern as your factored answer. So factor this 4x squared minus 9 using your difference of squares pattern that we just illustrated here and is illustrated up here. So let's check your work here then. So always 2 parentheses. That's part of the pattern here, 1, 2. And square root of the front goes in the fronts, so 2x. Square root of the back goes in the back, so 3. And then one of them gets a plus sign, one of them gets a minus sign. All right, so hopefully you chose that correctly. If you didn't, make sure you correct it and reach out to me if you have questions about what you did wrong. C, now I'm going to check. So it's a binomial, so I'm checking this difference of squares. Does x squared have a perfect square root? Sure does, it's x. Does 16 have a perfect square root? Sure does, that's 4. Is it a minus in the middle? No, it is not. So, because this is not a minus, we cannot use this pattern. It's obviously not a PST because it's not a trinomial. So that means that this guy is not factorable. Sometimes they'll tell you to write prime because that's what we call something that isn't factorable. But this guy is not factorable. There is no such thing as a sum of squares, only difference of squares when we're factoring. So don't get tricked just because you see those numbers and or variables that have perfect square roots. This one is not factorable. All right, this next one is a trinomial. So we definitely should not be looking at the difference of squares pattern. We should be looking to see if it fits our PST pattern. So first thing we have to check in this PST pattern is my front a perfect square? So yes, y squared, square root of that is y. Then I look to check the back. Is it a perfect square with a plus sign? Notice that both of these, that last term has a plus on it. So plus, yep, and the square root of 9 is 3. Now I have to check the middle term. And what I'm checking is to see, it doesn't matter what the sign is because we have one, that has a plus and we have one that has a minus in the middle. But it matters whether it follows this pattern. Is that middle term 2 times each of those square roots? So basically, I'm looking to see, okay, is this 6y 2 times the front, which is y, times the back, which is 3. So 2 times y times 3 would be 6y. So that means, yes, this fits the pattern. Once you've checked it out and said, sure does fit the pattern, then that means that I'm going to go ahead and look at what my factored form should look like. Notice it's a single parenthesis with a squared on the end. So I'm going to do single parenthesis with a squared. The square root of the front goes in the front, so that would be a y. The sign of the middle term is what goes in the middle. So this is a minus, means this is a minus. And then in the back, it's just the square root of the back, so that would be my 3. So y minus 3 squared is how I would factor that. All right, so now we're going to look at E, also a trinomial, which means I'm looking for the same thing. So do I have square roots in front and back? This would be x, this would be 2, so that's a yes. In the middle, is that middle term 2 times these two things that we wrote down? So x times 2. 2 times x times 2 is 4x. So this is also a yes. So write it as a single parenthesis with a squared on it. Square root of the front goes in the front. Sine of the middle goes in the middle. And square root of the back goes in the back. So this factors into x plus 2 squared. All right, this last example here has an asterisk because this one you have to, even when we're looking for special polynomials. Factoring has kind of its own order of operations, and the first step of factoring is always GCF. So we need to look, and we'll teach you when we start mixing all of the factoring together, that you always have to do it in order. So first we look for a GCF, then we would look for special products. So here, all three of these terms are divisible by 2. There is not a variable GCF because I have a constant. Anytime you have a constant, there can't be a variable in the GCF. Here, in example 2b, we didn't have a constant. We still had an x squared on my last term. That's why it had a variable as part of it. So I take out the 2. What do I multiply 2 by to get 2x squared? That would be x squared. What do I multiply 2 by to get 12x? That would be 6x. And then what do I multiply 2 by to get 18? That would be 9. Now, this is where we teach you that just because you did one step of factoring doesn't mean that you're done. Because this that is left in my parentheses is further factorable. It's a trinomial, which means that we're looking at PST. So PST, I check it. Square root of x squared is x. Square root of 9 is 3. Is the middle 2 times x times 3? It sure is. So that means that this parenthesis here that I had after my 2 is now a PST and is going to factor as a single parenthesis squared. Now, when you had a GCF in step 1, you have to remember to bring that GCF down into your answer. So I know that I'm going to have the 2 in front and I'm going to have a single parenthesis squared. What you need to do now for your last task is to fill in what goes here. So I've already checked it for you. I've written the stuff above. Now you need to make it look like one of these square of a binomials, this PST pattern. So go ahead, finish the factoring that goes in this parenthesis, and then come back to check. Okay, so pattern tells us square root of the front goes in the front, so x was my square root. Sine of the middle goes in the middle, so that's a plus, and square root of the back goes in the back, which is a 3. So then that means my final answer here is 2 times x plus 3 squared. Okay, make sure you do all of your practice. Factoring, the only way to get better at it is to practice it yourself. Watching me is not going to help you get better. So you need to practice, learn from your mistakes, check your answers, all of those good things.